Imagine just for a second that you have a multi-million-dollar, completely irreplaceable piece of technology.
Oh, yeah. Like somebody you absolutely cannot afford to lose.
Exactly. And it's not just, any random piece of tech. This thing has served humanity flawlessly for 2 solid decades. I mean, it has literally rewritten textbooks,
Yeah.
but right now, as we speak, it is slowly, silently falling from the sky.
Which is just a terrifying concept when you really think about it.
Right, and here's the kicker. You have exactly 9 months to catch it. You have to catch this, fragile spinning bullet that is moving at 17,000 miles per hour, or it just burns up in the atmosphere forever.
Yeah, and that ticking clock, uh, it isn't a hypothetical. I mean, that was the exact impossible reality facing the team trying to rescue the Neil Gehrels Swift Observatory.
Yeah.
And, to actually pull it off, they had to completely break how aerospace engineering works, just fundamentally dismantle it.
Welcome to our deep dive into what's been called the 9-month miracle. We are going to map out exactly how that happened, the massive shift from traditional human engineering to artificial intelligence and, the physical limitations that almost derailed the whole thing.
It is such a fascinating case study. The time frame alone, 9 months makes this one of the most intense engineering challenges of the modern era.
Because usually, 9 months gets you a couple of meetings?
Barely. In the traditional aerospace world, 9 months barely gets you through a preliminary design review. To go from a blank sheet of paper to a fully autonomous flying robotic capture vehicle in that window, well, it requires abandoning almost every legacy paradigm we have.
So before we get to the actual rescue and the AI of it all, we really have to look at what was falling. The Neil Gehrels Swift Observatory. It was launched in November 2004, and for 20 years, it's basically been our cosmic sentinel for gamma ray bursts, which are the most violent explosions in the universe.
Yeah, and it fundamentally changed astrophysics. Before Swift, detecting a gamma ray burst, which, by the way, is the cataclysmic death of a massive star, or, the merger of two ultra-dense neutron stars.
Right, the stuff that goes boom in the night.
Exactly. Catching those used to be mostly just a matter of luck. These flashes of radiation are incomprehensibly powerful. Sometimes they outshine the entire galaxies. But the thing is, they only last for milliseconds to maybe a few minutes.
Wow. So you can't really just, point a telescope and wait around.
No, not at all. By the time someone on Earth actually realizes a burst happened, it's already gone. Which is why Swift was so revolutionary. It wasn't just a regular camera. It was an autonomous hunting machine.
That sounds intense. How did it hunt exactly?
Well, it had a wide field sensor to detect the flash. And then, completely on its own, it would physically pivot its high-resolution X-ray and ultraviolet telescopes to stare directly at the afterglow before it faded. And it did this in seconds.
That speed is just incredible. And that's what allowed scientists to finally figure out the whole heavy elements mystery, right?
Yes, precisely. There was this long-standing debate in physics about where elements heavier than iron actually come from. Because a normal star's core fusion, it just stops at iron.
Right, so where does all the other stuff come from?
Exactly. To forge something denser like gold or platinum or, uranium, it requires an environment so extreme it almost defies description. And Swift gave us the definitive observational proof that these elements are forged in the crucible of colliding neutron stars.
That is wild.
Yeah, the gold in human jewelry or the rare earth metals powering the electronics you use every day, Swift literally traced their origin back to those specific cosmic anvils.
It's profound, honestly, when you realize it's mapping the origins of the materials that make up our world. So, okay, Swift is up there doing this monumental work in this safe, near-vacuum orbit about 370 miles above Earth, and it's been pristine for 2 decades.
Coasting along perfectly.
Right. But then, late 2024 rolls around, and the problem doesn't even come from the satellite itself. There's no mechanical failure. The threat comes from our own star.
Right. Solar cycle 25. It reached a highly active solar maximum. The sun operates on these roughly 11-year cycles of magnetic activity. And at the peak, it just ejects massive amounts of extreme ultraviolet radiation, high-energy particles, and solar flares.
See, I think if you're listening to this, you might assume space weather just means, nice auroras or maybe some static on your radio.
Yeah, that's a common misconception.
Yeah.
But it actually alters the physical dimensions of Earth's atmosphere.
Wait, it physically changes the atmosphere?
Yes. And that's the core mechanism of this whole crisis. When that extreme ultraviolet radiation bombards the thermosphere, which is the upper layer of our atmosphere, it transfers energy to the gas molecules, primarily atomic oxygen.
Okay, so the molecules heat up.
Exactly. They heat up, their kinetic energy increases, and the gas physically expands outward. So denser layers of the atmosphere are basically pushed to much higher altitudes than normal.
Which means Swift, sitting up at 370 miles, is suddenly flying through this thicker soup of molecules. I always think of it like running. Running in waist-deep water is exhausting compared to running on dry land. For 20 years, Swift has been coasting on a dry track, and suddenly the sun just floods the track.
That's a great analogy. It started hitting serious aerodynamic drag. And because Swift is an older satellite, it has no onboard propulsion system. It has reaction wheels to turn and point its telescope, sure, but it has no engine to actually push itself forward.
So it's basically just a heavy box that can spin, but can't accelerate.
Right. It relies entirely on its initial launch velocity from all the way back in 2004. And orbital mechanics dictate that if you induce drag on a spacecraft, even microscopic drag from highly dispersed oxygen atoms, you bleed kinetic energy.
And when you lose speed, you fall.
Exactly. When velocity decreases, altitude decreases. And it's an exponential decay curve, because as you drop lower, the atmosphere becomes even denser, which increases the drag further. So by mid-2025, predictive models showed Swift was sinking fast.
The models put it crossing this fatal threshold about 186 miles up by October 2026. That was the point of no return. Once it hits that density, it tumbles, the solar panels shear off, and it just incinerates in the lower atmosphere.
Just a complete fiery loss of the instrument.
Right. So we have this absolute unmoving deadline, and that triggers NASA to award a $30 million contract to Katalyst Space Technologies. They're this small aerospace startup, and their mission is to build a robotic servicer named Link to fly up, catch Swift, and boost it back to safety in 9 months.
Which, again, in the legacy aerospace world, is considered theoretically impossible.
Yeah, catching something in orbit isn't like matching speeds on a highway, is it?
Not even close. Rendezvous and proximity operations, or RPO, is incredibly unforgiving. The sheer velocity is the first hurdle. Like you said, Swift is moving at 17,000 miles per hour, so Link has to launch, match the exact orbital plane, and synchronize its speed down to millimeters per second.
Millimeters per second at 17,000 miles an hour.
Yeah. But the actual nightmare isn't the speed. It's the nature of the target itself. Swift is entirely uncooperative.
Meaning it doesn't want to be caught. Well, it wasn't built to be caught. It was built in an era when satellites were single use. You launch it, does its job, it dies. So there are no docking ports, no magnetic capture plates, no little reflective targets to help a laser guidance system lock on.
Nothing. Plus, Katalyst CEO pointed out this glaring blind spot during the project. He said nobody took high-resolution reference photos of Swift's aft end before it launched. The CAD models from 20 years ago don't reflect the as-built reality.
Wait, really? They didn't even know what the back of it looked like?
Not exactly. Thermal blankets shift during launch. Materials degrade over 2 decades of harsh solar radiation. It looks different now than it did on paper in 2004.
Wow. So Link is flying blind toward a target moving at 5 miles a second. And it doesn't even have a good picture of the target's bumper. And to make it worse, you can't just fly it manually from the ground. I've seen people fly drones with those VR headsets, but that doesn't work in space, right?
Right, because of light speed latency. Even a 1-second radio delay between Earth and orbit means by the time you see the camera feed on your monitor, the satellite has already moved. If you push the joystick to thrust left, your command arrives too late and you crash.
You just smash into a priceless telescope. So the whole capture sequence has to be completely autonomous. The robotic servicer has to look at the target, calculate the math, make decisions, and actually fire the thrusters in real time, all without a human doing anything.
Exactly. And to do this, Link uses time-of-flight LiDAR. So it pulses lasers at the target and measures the exact time it takes for the photons to bounce back. And since the speed of light is a constant, it can instantly calculate the distance to thousands of points on the surface.
Which creates a 3D point cloud.
Right. A highly dense 3D point cloud.
But a point cloud is just raw geometry, isn't it? It's basically millions of blind data points. The computer has to somehow recognize what part of the satellite it's looking at, compare that really noisy point cloud to a 20-year-old blueprint, and then figure out where to grab.
Yeah, that's the perception challenge. And what it's actually trying to grab is fascinating. The engineers programmed Lin Den to target these 3 specific ground-handling brackets.
And these brackets, they weren't meant for space, right?
No, not at all. They're essentially simple metal hoist rings bolted to the aft bulkhead. Their sole purpose was just to allow a crane to lift the observatory inside the clean room back on Earth before launch. They were never, ever designed to bear loads in a microgravity environment, let alone be manipulated by robotic grippers.
This is where the physics of the grab seem almost impossible to me. Swift isn't perfectly still up there. It has this residual rotation. So Amante has to extend these three robotic arms, track these small spinning crane rings, and grab them. I mean, if you grab a spinning top by its rim, you have to match its spin perfectly or you mess it up.
That's exactly the risk. If one of those robotic arms pushes slightly too early or applies even a tiny bit of asymmetric force, you impart torque. And in a frictionless vacuum, that torque sends the entire 1.5-ton observatory into an uncontrollable tumble.
Which would be catastrophic.
Beyond catastrophic. The force feedback algorithms have to be absolutely flawless. As the grippers close, they must apply perfectly symmetrical pressure across all three contact points simultaneously while continuously matching the target's rotation. If they induce a tumble, the mission is over. Swift's fragile solar arrays would likely just snap off from the centrifugal force.
Okay, so the big question here is how do you design the physical hardware for those delicate arms and write the flawlessly precise software to execute that maneuver in just 9 months? And the answer is Katalyst didn't engineer this the way humans have engineered for the last century.
Right. They handed the heavy lifting over to artificial intelligence.
They completely discarded the legacy pipeline. Instead of human engineers acting as the primary synthesizers of design, AI became an active co-pilot. And this isn't just about working faster, it's a fundamental shift in how we create things, starting with the physical structure of the spacecraft itself.
Let's look at those robotic arms as an example. They need an extreme strength-to-weight ratio. They have to survive the incredibly violent acoustic vibrations of a Pegasus XL rocket launch, and they have to physically push a 1.5-ton object in orbit.
Normally, an engineer draws a bracket, runs a stress simulation over a few days, finds the weak point, adds some metal, and repeats the process, right? A very slow manual loop.
Exactly. It's tedious. But Katalyst utilized structural generative design, specifically topology optimization algorithms.
How does that work?
Well, the human engineer just defines the boundary conditions. You input the exact load vectors, basically saying, hey, this arm will experience 500 newtons of force in the x-axis and 200 in the y-axis. Then you define the forbidden volumes, meaning areas where the structure absolutely cannot intersect with things like cameras or star trackers.
Right. And you also input the manufacturing constraints. They told the AI, whatever crazy design you come up with, we have to be able to manufacture it immediately using a 5-axis CNC mill or by 3D printing it in titanium.
Exactly. And then the algorithm just takes over. It meshes the available volume into thousands of tiny blocks called voxels. It runs a simulation and iteratively removes the voxels that experience the least strain energy. It just continuously hollows out the material until only the absolute minimum required structure remains to support those loads.
Which results in these brackets that look, honestly, incredibly alien. The term the source used is biomimetic. Instead of right angles and solid blocks of metal, the AI spits out something that looks like an avian bone structure.
Yeah, it's stringy, curved, and heavily webbed.
It puts material exactly where the stress flows and literally nowhere else. It's like evolutionary biology on fast forward.
That's a perfect way to put it. Nature optimizes for material efficiency because biological mass has a high metabolic cost. The algorithm optimizes for material efficiency because launch mass has a huge financial and physical cost. The mathematical optimization pathways are identical, which is why the results look so organic.
It's mind-blowing.
It really is. An AI generated a titanium structure that was lighter and stiffer than any human intuition could produce, and it did it in a matter of hours. That alone shaved months off the hardware schedule.
But having a lightweight robotic arm is kind of useless if the brain controlling it miscalculates the grip, right? And testing that software, the guidance, navigation, and control, or GNC, that is usually what stalls aerospace projects for years.
You can't exactly just push an over-the-air update if the code crashes while you're grabbing a satellite.
No, absolutely not. Traditionally, validating the GNC software requires extensive hardware in the loop, or HWIL testing.
Hardware in the loop. Right. You have to build a physical, full-scale mock-up of the robotic servicer and the target satellite. You place the surfacer on these precision air bearings on a massive flat floor so it floats seamlessly, simulating microgravity. You integrate the actual flight computers, the sensors, the cold gas thrusters, and you physically execute the docking maneuvers over and over again.
I mean, it sounds like it would take years just to build the test rig alone.
It does. And Katalyst didn't have years, so they bypassed the physical lab entirely by building a digital twin.
A digital twin. Let's unpack that, because it's not just a nice 3D animation, is it?
No, a digital twin is a hyper-fidelity simulation environment. It is governed by rigorous orbital mechanics, rigid body dynamics, and accurate sensor emulation. They essentially built a perfect digital replica of both LNK and Swift inside the computer.
And here is where the machine learning really shines. They didn't just program a rigid path for the robot to follow. They let the AI fly the mission millions of times in the simulation using reinforcement learning. And they actively tried to break it, didn't they?
Oh yeah. They systematically tortured the control algorithms. They injected random sensor noise into the simulated lidar. They simulated massive solar flares temporarily blinding the optical cameras. They introduced latency into the thruster valves, just an immense matrix of edge cases.
Because a human programmer couldn't possibly anticipate every combination of a sensor failing while the atmosphere randomly thickens.
Exactly. But the machine learning model experiences all these failures, learns from the resulting tumbles, and mathematically refines its recovery strategies over millions of iterations.
But wait, the output of a machine learning model isn't traditional code, is it? It's a neural network, a sort of black box of wints and biases. How do you actually get that onto a spacecraft flight computer that requires highly deterministic, auditable code? You can't just fly a black box and hope for the best.
Right, and that is the crucial final step of their software pipeline. They utilize auto-coding suites to translate the successful trained control policies directly into deterministic, flight-ready C++ code.
Oh, wow. So it writes its own C++ code.
Yes. Furthermore, the AI auto-generates the accompanying unit tests. This eliminates the tedious, error-prone process of a human manually translating a complex control theory into thousands of lines of syntax, and it catches edge case bugs that human developers routinely miss.
So just to recap, the AI designs the bones of the ship, it learns how to fly the mission, and it writes its own flight code.
That's the 9-month miracle.
It's unbelievable. But, they still had to buy the actual physical engines and computers. They used COTS components, which stands for commercial off-the-shelf parts. And the thrusters they bought are really interesting. They're xenon-fueled Hall effect thrusters. Now, I know chemical rockets burn fuel and shoot fire out the back, but how does a Hall effect thruster work, and why did they use it for this mission?
Well, chemical rockets provide high thrust, but they have terrible fuel efficiency. For an orbital surfacer that needs to make highly precise adjustments and push a massive payload over a long period, you need high efficiency, or what we call specific impulse. A Hall effect thruster uses an electric field to ionize a noble gas, typically xenon.
So it basically strips the electrons off the xenon atoms.
Exactly. It creates a radial magnetic field that traps electrons in a circular motion, which is the Hall current. When the neutral xenon gas is injected into this ring of electrons, the collisions strip away electrons, turning the xenon into positive ions. Then, a powerful electric field accelerates these heavy ions out the back of the thruster at extreme velocities.
But it doesn't give a huge push, does it?
No, it produces very low thrust. Sometimes it's equivalent to the weight of a piece of paper resting in your hand. But the key is, it can fire continuously for months, providing immense cumulative velocity.
The tortoise and the hare, basically. But the challenge with buying a Hall effect thruster from one company, a flight computer from another, and an optical camera from a third is integration. Normally, you bolt them all into the spacecraft bus, turn it on, and realize, oops, the magnetic field from the thruster is scrambling the computer, or the heat from the power unit is melting the camera mount.
Yeah, integration is historically where schedules completely collapse. Discovering an electromagnetic interference or a thermal conduction issue during physical assembly forces a massive redesign of the chassis. But Katalyst preempted this using multi-domain system modeling.
Meaning they aren't just simulating the physics of the flight, they are simulating the heat and the electricity simultaneously in the software.
Exactly. The AI models the thermal dissipation profiles of every single circuit board and the electrical transients of every power cycle. It mathematically predicts how the heat from that Hall effect thruster will propagate through those generative titanium brackets and how it will affect the optical sensors, all before a single piece of metal is cut.
And we know this AI modeling wasn't just theoretical because of what happened when the physical parts were finally assembled and shipped to NASA Goddard for TVA testing.
Oh, this part is legendary.
Yeah. For those listening, thermal vacuum testing, or TVAC, is where a spacecraft is put in a massive vacuum chamber, baked with extreme heat to simulate the sun, and frozen with liquid nitrogen to simulate Earth's shadow. It's notoriously brutal. Satellites almost always fail their first TVAC run because, thermal expansion warps a board or snaps a wire.
But LANK passed Goddard's vibration and TVAC test on the very first attempt.
On the first try? That's insane.
It is. A 100% pass rate on initial integration is virtually unprecedented in the aerospace industry. It is the definitive proof that multi-domain digital simulation can completely replace iterative physical testing.
So we have this absolute triumph of digital engineering. The lifeboat is being built at record speed, but there's a glaring physical reality that AI cannot solve. You can accelerate the design, you can accelerate the code generation, but you cannot accelerate the physical manufacturing and launch logistics beyond a certain point. It still takes time to bolt the rocket together and secure a launch pad. And while Katalyst is working these miracles, the Earth's thermosphere doesn't care. Swift was falling faster than anticipated.
Yeah, by December 2025, the telemetry coming down from Swift was undeniable. The density of the expanded atmosphere was creating immense drag, and the orbital decay curve suddenly steepened.
Meaning it was dropping faster.
Much faster. The mathematical projections showed Swift crossing that 186-mile death line before LNK would be ready to launch. So the AI was building the rescue ship, but the ship was going to arrive at an empty patch of sky.
This is where the story shifts back to human ingenuity. The flight operations team at Pennsylvania State University, who had been actually operating Swift for 2 decades, realized they had to buy Katalyst more time. They had to somehow slow down a falling 1.5-ton box that has no brakes and no engine. How do you even do that?
They approach the problem through the lens of fluid dynamics. I mean, in the thin upper atmosphere, spacecraft don't usually worry about aerodynamics. But in the swollen thermosphere, the atmosphere acts as a highly rarefied fluid. And in fluid dynamics, drag is directly proportional to the cross-sectional area exposed to the flow.
So every square centimeter of the spacecraft that is perpendicular to the direction it's flying functions as a parachute.
Precisely.
So if you want to fall slower, you have to shrink your parachute. But Swift is shaped like a giant, awkward box with massive solar panels sticking out. You can't exactly change its shape up in orbit.
You can't change its physical shape, no, but you can change its orientation. The Penn State team initiated this radical drag reduction campaign. They had to alter the fundamental operation of the telescope. Instead of autonomously slewing to observe whatever gamma-ray burst appeared, they restricted the observation angles. They intentionally flew the observatory in a highly streamlined attitude, pointing it like a dart into the oncoming molecular wind just to minimize its cross-sectional area.
They sacrificed about 25% of their scientific targets just to keep the spacecraft in this aerodynamic posture. But even that wasn't enough, was it? The drag was still pulling it down.
No, it wasn't enough. By April 2026, the situation became so critical they had to make decisions that must have been absolutely heartbreaking for the scientific community. To reduce the surface area further, they had to address the largest parachutes on the spacecraft, the solar arrays.
The panels.
Right. They decided to feather the solar arrays. They commanded the mechanisms to rotate the massive panels so they were edge-on to the velocity vector, literally slicing through the residual atmosphere like the blade of a knife.
But wait, if the panels are edge-on to the direction of travel, they are no longer optimally tracking the sun. So the power generation just plummets, right?
It drops drastically. And to prevent the spacecraft's batteries from draining, which would cause a total loss of attitude control and instant tumbling, they had to drastically reduce power consumption.
So what did they turn off?
They deactivated the primary scientific instruments. They turned off the ultraviolet optical telescope. They powered down the burst alert telescope.
Oh, wow. They intentionally blinded their own sentinel. An instrument that had scanned the cosmos flawlessly for 20 years was shut down just to save the physical chassis. That is a massive operational sacrifice. But the fluid dynamics trick worked.
It did. The reduction in drag was significant enough to alter the decay curve. By flying it in that aerodynamic dart configuration and feathering the arrays, they pushed the critical survival margin back. They shifted the projected re-entry date from June 2026 out to September 2026.
They bought exactly 3 months, 3 extra months of breathing room for the engineers at Katalyst to finish integration, test the AI algorithms, and get the servicer onto the Pegasus rocket. It is the ultimate synergy, really. The AI built the lifeboat faster than humanly possible, but human operational agility kept the sinking ship afloat just long enough for it to matter.
It's a beautiful way to look at it, and it highlights a critical realization. AI did not replace the engineering team. It fundamentally elevated them. But, this total disruption of the workflow where AI is generating the geometry, writing the C++ code, and predicting the thermodynamics, it forces a huge reckoning within the engineering community. If the machine is doing all the synthesis, what exactly is the human doing?
Yeah, the source material focuses heavily on this pedagogical shift. For decades, STEM education, science, technology, engineering, and math was built on the premise that the human brain was the primary calculator. You go to engineering school and you spend 4 years learning how to manually derive complex differential equations, or how to calculate finite element stress tensors on a structural truss, or write low-level boilerplate code.
Historically, the ability to execute highly localized manual calculations was the primary bottleneck of innovation. You needed thousands of engineers sitting in rooms with slide rules or early CAD programs simply to verify the math. The education system trained synthesizers humans capable of meticulously constructing a system, component by component.
But the LENK mission proves that manual calculation is pretty much obsolete as a primary skill. AI can iterate thousands of structural geometries in an hour. It can auto-generate unit-tested code. The human is no longer the bottleneck for calculations, so the modern engineer has to transition from being a synthesizer to being a systems architect.
Exactly. The required skill set has fundamentally migrated. An engineering student today must learn how to orchestrate the AI tools. This means developing deep expertise in defining boundary conditions and stating highly specific optimization goals.
Right. You don't need to manually draft the robotic bracket. You need to understand the physics well enough to tell the AI exactly what loads that bracket must survive and what materials it is constrained by. It sounds like the difference between playing an instrument and conducting the entire orchestra.
That's a great way to think about it.
But the conductor still needs to know if the brass section is out of tune, right? Which brings up validation and verification, or V&V. If the AI is generating code and these alien bone structures, how do you know it isn't making a catastrophic mistake?
This is arguably the most dangerous aspect of AI-augmented engineering. AI algorithms optimize purely for the mathematical constraints they are given. They possess no common sense, no intuition, and no inherent understanding of physical reality.
Yeah.
They can and do hallucinate.
So if you tell the topology optimization algorithm to make a bracket as light as possible to hold 500 newtons of force, it will mathematically find the absolute minimum amount of titanium needed. But if you forget to input the thermal contraction parameters for the extreme cold of Earth's shadow, the AI won't remind you.
Exactly. It will just output a bracket that is perfectly strong at room temperature but snaps the second it gets cold in space. Precisely. The AI assumes your constraints are comprehensive. Therefore, the primary survival skill for a modern engineer is mastering validation and verification. You must know how to design robust adversarial test suites to stress test the AI's output. You have to be able to look at a simulated model and spot systemic anomalies that the machine learning algorithm optimized around rather than actually solved.
So you are no longer doing the math yourself. You are critically interrogating the math of an entity that is vastly faster than you, but completely blind to context.
Yes, and that requires a much broader understanding of how all the pieces fit together. In traditional university engineering programs, everything is heavily siloed. The mechanical engineers stay in their building and design the chassis. The electrical engineers design the wiring harness. The computer scientists write the code.
Right, and they usually don't interact until the final senior project, which is usually when they realize the mechanical engineer placed a solid aluminum strut right where the electrical engineer needed to run a data cable.
Exactly. Siloed education produces specialists who struggle with emergent system-level failures. Space systems are highly coupled. A structural vibration during launch affects the optical sensor alignment, which affects the guidance software, which triggers a thruster, which generates heat, which expands the structure. It is a continuous feedback loop spanning multiple physics domains.
So academia has to adapt. They have to train students using the same multi-domain AI platforms that Katalyst used, where you simulate the thermodynamics, orbital mechanics, and electrical networks simultaneously. You have to train systems thinkers who understand the entire web of dependencies.
It really is an imperative for survival in the modern aerospace industry.
Yeah.
The engineers who saved Swift weren't just coding or machining. They were orchestrating a symphony of AI tools across every physical domain to bend the timeline of reality.
Which brings us to the present moment. Right now, as you listen to this, the LINK robotic servicer, entirely designed and built through this new paradigm, is sitting inside the fairing of a Pegasus XL rocket out at the Kwajalein Atoll in the Pacific Ocean. It's waiting for the precise launch window to fly up, autonomously navigate the point clouds, match the rotation of the ground handling brackets, and physically catch a falling observatory.
It is an incredible technological thriller.
It really is. But looking beyond this one mission, what does this actually mean for global infrastructure? Katalyst was awarded $30 million for this. That sounds like a lot of money to an average person, but in space terms, it's practically a rounding error, right?
Oh, absolutely.
Yeah.
The return on investment is staggering, and it signals a new era for public goods in orbit. To design, build, and launch a modern replacement for the Swift Observatory, an instrument with comparable autonomous slewing capabilities and multispectral sensors, it would easily exceed $500 million, perhaps even approaching $1 billion.
Not to mention the decade it would take to build it, during which time astrophysicists have zero data on gamma ray bursts.
Right. But by leveraging AI-augmented engineering, a small private startup was able to develop a highly complex robotic servicer for a fraction of that cost. They are extending the operational lifespan of a priceless scientific asset for another decade, ensuring continuous data collection, all for $30 million. It completely rewrites the economic calculus of space operations.
The CEO of Katalyst referred to this capability as on-demand orbital servicing. And I think about the implications for all the other vital infrastructure we rely on. I mean, we have billions of dollars of satellites up there managing global GPS, predicting severe weather, handling international telecommunications.
Historically, when one of those highly expensive assets suffered a minor mechanical failure, ran out of station-keeping propellant, or experienced a slight orbital decay, the entire multi-ton satellite was just written off. It was either abandoned to become dangerous space debris or deliberately deorbited to burn up in the atmosphere. We treated incredibly complex spacecraft as disposable items.
But if you can design and launch a custom robotic servicer in 9 months, space is no longer a disposable economy.
Exactly. We transition to an era of maintainable, renewable infrastructure. We can refuel weather satellites, repair jammed solar arrays on communications hubs, or attach propulsion modules to legacy assets to safely deorbit them, mitigating the massive crisis of space debris. The methodology pioneered here proves that we do not have to accept the loss of critical orbital assets.
It is a profound shift in how we manage our footprint in space, but it also leaves me with a final, slightly staggering thought. We've spent this entire time marveling at how this AI-accelerated process was used to build a lifeboat. 9 months from a contract signature to a fully autonomous rescue ship on a launch pad. It was born out of absolute necessity to save legacy infrastructure. But what happens when we remove the crisis? What happens when we take this incredible, rapid, AI-driven manufacturing capability and apply it not just to fixing old telescopes, but to building the next generation of technology?
Oh, the extrapolation is profound. It removes the primary barrier to orbital expansion, which is time.
Exactly. If the timeline from concept to multi-domain simulation to auto-coded software to biomimetic structural printing is suddenly reduced from decades to a matter of months, how radically will the architecture of Earth orbit change in our lifetimes? We aren't just talking about refueling satellites anymore. We could be talking about deploying kilometer-wide solar power arrays, assembling modular orbital habitats, or constructing massive deep space scientific interferometers at a speed that previously belonged purely to science fiction. If an algorithm can figure out how to catch a 17,000-mile-per-hour bullet in 9 months, the limits of what we can construct in microgravity have fundamentally disappeared.
It suggests that the bottleneck is no longer human engineering capacity, but simply our imagination and our willingness to trust the systems we orchestrate.
It's a completely new horizon. Well, we want to thank you for joining us on this deep dive into the 9-month miracle. It is a testament to what happens when we abandon legacy thinking, harness the absolute cutting edge of artificial intelligence, and refuse to accept the impossible. Keep your eyes on the skies, stay curious, and keep questioning the limits of what we can build. Because somewhere up there, an irreplaceable sentinel is falling through the atmosphere, and a robotic catcher's mitt designed by an AI and built by human ingenuity is waiting on a launch pad to rewrite history.